All right, so last class we talked about the ideal gas law. In the ideal gas law, we have PV equals nRT, and we looked at how each of those variables are impacted by the others. Are they directly or indirectly related? Do they have a positive or negative slope? What happens, and how do I find that missing variable? Today we're going to talk about the combined gas law. This takes all of our gas laws that we're going to talk about this unit and combines them into one single law called the combined gas law. All right, what we're going to do is relate two sets of conditions for pressure, volume, and temperature to each other and compare how those things change as variables are adjusted. So if you look here, you have P1 times V1 over T1, so that is your initial conditions. This is what we start out at. Maybe I start at 2 ATMs at a volume of 3 liters and temperature of 298 Kelvin. And then I look at if I change my pressure, maybe I change pressure to 5 ATMs, and my volume changes to 3 liters. What would my new temperature be? So that would be your final conditions. So we're looking at how do our variables respond to different changes. So remember, temperature must always be in Kelvin. When you are working out gas law problems, temperature has to be in Kelvin. So remember, that is Celsius plus 273. At no point during Unit 6 will you plug in temperature as Celsius. All right, you must always be in Kelvin. But notice here, when we talked about the ideal gas law, you had a few other reminders, such as volume had to be in liters. But you don't see that this time, right? There's no reminder telling you that. Why do you think? What else are we missing from this? We're missing our R value, or the gas constant. So we do not have a gas constant in the combined gas law. Therefore, I no longer have the units of that gas law, for instance, liters, ATM per molar Kelvin, impacting what units I have to use in my equation. So you're no longer limited to liters. You no longer have an R value or a gas constant. Therefore, you can use any unit of measurement for volume, any unit of measurement for pressure. The only key is they have to be the same. So if volume on the left is in liters, then your volume on the right must be in liters. If volume in the left is centimeters cubed, then volume on the right would need to be in centimeters cubed. And same thing with pressure. If pressure on the left was ATMs, then pressure on the right would need to be ATMs. If it was kPa, the right would need to be kPa. So again, it doesn't matter what units you use for pressure and volume as long as they are the same. Temperature though, temperature must always be in Kelvin. All right, so how do we do these problems? Step 1, identify what is given to you in the problem. All of your gas law work, you should always identify your variables. Take some time to list out those variables and what is given to you in the equation or in the problem so that you don't make any mistakes as you're working through it. So for some problems, that'll be really easy. It'll say, hey, I start out with these conditions and the ending conditions are this. Find the missing variable. But in others, you got to read through and make sure you interpret the problem. So some things to look for. If it is the first set of conditions, you'll say, hey, it was initially at 2 kPas and 3 liters. Or it begins at 2 kPas and 3 liters. Or it starts at 2 kPas and 3 liters. And then some clues that something has changed is secondly, or then, we measure it again and I have 6 kPas at 1 liter. Or after increasing the temperature, or my new volume was, and so those are some clues that that is the final set of conditions in your problem. So look for that verb. If something is happening, you have an initial and then final situation. Cross out any variables you don't need. So this will be anything that stays constant. Variables equation. So if we look at our equation, PV over T equals PV over T, that therefore means if my temperature stays the same, say at 298 and 298, then my pressure and volume would not be impacted by temperature. So why would I include that in my math problem if it's not going to tell me anything important? So then I could just erase temperature because temperature stays the same. So anything that stays constant or isn't talked about is not relevant or imperative to your problems, to your calculations. And then rearrange that equation for what you don't know and solve algebraically. So let's look at a first example. A gas tank has a volume of 28.1 decimeters cubed and a pressure of 18.4 ATMs. The temperature is 32 degrees Celsius. Temperature equals 32 degrees. What is the temperature? So I want to know, what is my new temperature in Celsius when the gas is put in a 11.2 liter tank with a pressure of 22.7 ATMs. So notice my volume and my pressure changed, and I want to find the new temperature. So the first thing you should have done is listed out those variables just like I did. Then we need to evaluate our units. Are they in acceptable units to be able to plug it into our equation? So we notice that pressure matches ATM and ATM. Volume, decimeters cubed in liters. Remember, those are equal to each other. And then temperature. What's wrong with temperature here? It must be in Kelvin. That's in Celsius. So we need to add 273 to get our new temperature of 305 Kelvin. I can use that to plug into my equation. So here I have P1 V1 equals over T1 equals P2 V2 over T2. All right, so we're just going to plug it right in, plug those values in. So P1, V1, and T1. And same thing on the right. So here you see those values plugged in. 18.4 times 28.1 over a temperature of 305 Kelvin equals 22.7 times 11.2 over that new temperature I'm trying to find. All right, so when you get to here, how do we solve for that variable? It's on the bottom. So let's get rid of our division. We're going to do that by cross multiplying. All right, so when you cross multiply, you basically make a big X through what you have. And everything that goes through that line goes on a side together. So you will see 305, 22.7, and 11.2 together on one side. All right, here it is. And then you would see 18.4, 28.1, and T2 together on one side. So now that we've gotten it out of our fractions, our division, we can now simplify. So I'm going to simplify all of these numbers on my left and right and combine like terms. I've got 517.04 T2 equals 77,543.2. All right, solving for T, I need to divide by 517.04 so that it cancels out on the left. And my T2 value equals 149.98. And that temperature is in Kelvin. What do we notice the problem asked for? The problem asked for temperature in Celsius. So I'm not done yet. The problem asked for it in Celsius, so I need to subtract 273 to get back to Celsius, and that gives me a final answer of negative 123.02 degrees Celsius. It's example 1. Let's look at example 2. A balloon is filled with 25 liters of air. So my volume is 25 liters at 1 atm of pressure. So pressure is 1 atm. If the pressure is changed, so that tells me this is scenario 2. So pressure is changed to 1.5 atms. What is the new volume? So listing out those variables, we notice that I don't have a temperature. So your ATMs are the same value, you're good to go, and you're solving for volume in liters. So right here, cross out the variables you don't need. I don't need temperature. When they don't talk about it, that means it's staying constant. It's not imperative to your equation. All right, so here was my original combined gas law. I can mark out temperature, and I'm just using PV equals PV2. So we're going to plug into that equation. Got 1 ATM times 25 liters equals 1.5 ATMs times volume. So combine like terms and simplify. I've got 25 equals 1.5 V. As we know, in order to get V by itself, I need to move 1.5 to the other side. So I'm going to divide by 1.5 on both sides. It cancels out of the right and leaves me with 16.67 liters as my final volume. Third example. A gas is collected in a 242 centimeters cubed container. So volume is 242 centimeters cubed. The pressure of the container is measured and determined to be 87.6 kPas. What is the volume? So I'm looking for a new V of the gas at standard pressure. Wait, what is standard pressure? If we think back, remember that's at sea level, so 1 atm or 760 torrs slash mmHg, either one. It's also equal to 14.7 psis. And lastly, standard pressure for kPa is 101.325. All right, so it's asking us to find pressure or find volume at the standard pressure. So 101.325 kPas. My units are the same. I'm solving for volume in centimeters cubed. As we notice in this one again, we did not talk about temperature. Therefore, cross out those variables that you don't need. I don't need temperature. So we're going to pick a formula, and that formula is just PV equals PV2. So there you see your temperature go away. So let's plug those values in. 87.6 times 242 equals, over on my second side, 101.325 times that volume that I'm solving for. So when we combine like terms and simplify, on the left, I get 21,199.2. And on the right, I haven't been able to simplify anything. So in order to solve for V, I need to get V by itself, which means I'm dividing by 101.325. Those cancel. And once you divide, you are left with 209.22 centimeters cubed for your volume. How do we know what this unit is? It's always going to match the unit from the other side. So if this is centimeters cubed, then your answer must be in centimeters cubed. Let's take a look at another example. What is the temperature of a gas that is expanded from? So it's expanded from, that means this is where it started at. A volume of 2 liters at 25 degrees Celsius to 4.1 liters at constant pressure. So pressure does not change. I don't need to worry about pressure. It's not going to impact those variables. So here's what I'm looking for. You should have identified your variables that we don't have pressure. And we look, our volume is in the same units, liters and liters, so we are good to go. And temperature though, temperature is in Celsius. It needs to be in Kelvin. So Kelvin equals Celsius plus 273. And that we get to be 298. All right, so mark out those variables we don't need. We notice that P is not there, so I can mark out P from my equation, right? Because constant means P would be the same on both sides. Therefore, it is not going to affect anything. So when we take away P, I just have V1 over T1 equals V2 over T2. Plugging into your equation, we're going to plug in our V and T, and here's what you have. 2 over 298 equals 4.1 over T2. Again, here we have our fractions. We have our division. We need to get out everything out of the bottom. So, cross multiply. Again, when you cross multiply, everything from that one diagonal is going to go together, and everything from the other one is going to go together on the other side. So here you see your 2t times 4.1, equals 4.1 times 298. And so simplify, combine like terms, 4.1 times 298 is 1,221.8. Then we need to get t by itself, so we're going to divide by 2. T equals 610.9. And temperature, again, is always in Kelvin. What we plugged in was in Kelvin, so what we get out is going to be in Kelvin. All right, it doesn't specify what unit it wants temperature in, so you can leave it in Kelvin. You do not need to convert back to Celsius. And let's take a look at one last example here. What is the pressure inside of a 0.250 liter can of deodorant Let's take a look at one last example here. What is the pressure inside of a 0.250 liter can of deodorant that starts at 25 degrees Celsius and 1.2 ATMs? That temperature is then raised to 100 degrees Celsius. So this is one of those where you have to read through the problem and see what's happening. All right, so it starts at 25 degrees and 1 ATM, and I want to know the pressure once the temperature is raised to 100 degrees Celsius. Now notice it tells us about volume. Well, let's think about that. It doesn't give us a second volume, so I can't solve for both, or it doesn't give us initial volume, so I can't solve for both volume and pressure. So that means volume has to be given to me. Well, let's think about this. If you look at it, it's a can. So we have a spray can of deodorant. Here's our spray can. There's a little knob at the top. All right, as I spray this, does the amount of space that this can takes up change? Because that's what volume is. Volume tells us how much space this can takes up. No, that can is forever the same size. It may be empty inside, but the can itself still takes up 0.250 liters of space. Think about if you drink a 2 liter from the store, right? If you drink a 2 liter, it's now empty, but that bottle itself can still hold 2 liters of fluid. So your volume is constant. All right? So we don't need volume. We get to mark it out. Because it's constant, it doesn't change, then we don't need it. So identify your other variables. Let's check them out. Temperatures both in Celsius and they need to be in Kelvin. So add 273 and you get 298 and 373 respectively. Now with our new temperatures, I have Kelvin and Kelvin, ATM and ATM. Good to go. If we look at volume, remember we don't need it because it was constant. Therefore, we can mark volume out of our equation. That means you have P1 over T1 equals P2 over T2. Our initial pressure and temperature should equal our final pressure and temperature. So go ahead and plug in 1.2 over 298 equals that second pressure over 373. Again, in order to get out of our fractions, let's go ahead and cross multiply. And when you do, you see that your 298P comes over here, and 1.2 times 373 goes on the left. Doesn't matter which side you put them on, 1.2 just has to be with 373, and 298 has to be with P2. So if you wrote it like this, it will be the same exact thing. All right, doesn't matter which side, it just means you have to write those things together. So, now that we have this, let's combine like terms and simplify. 1.2 times 373, get 447.6, and then divide by 298 in order to solve for P. Why is it ATMs? Because our initial was in ATMs, and so that means our final is also going to be in ATMs. All right? So that was the last example that we're going to work through together. You have two problems right here that you can try on your own. Take a second and pause the video and work these out on your own. And then once you play the video again, I will show you what your answers should be. So take a second and pause, work these problems out. All right, so now that you're done, you should have found that your temperature for number 5 is 579, and your temperature for number 6, your volume for number 6 should have been 4.9.